so in this one, we don't have anything we got to worry about in front of the second derivative. So we know our general solution is going to look like y equals summation n equals 0 to infinity of c sub n x to the nth. And so we can just actually specifically substitute that in, just converting each, so the second derivative and the first derivative into those power series conversions. So for the second derivative, I have summation of n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 minus x. So this would be n equals 1 of infinity. That's the first derivative, and that would be an n there, and that's c sub n of x to the n minus 1 plus 2, and then that's n equals 0 to infinity c sub n of x to the nth. Okay, so then from here, I want to absorb in that x into that second term there. So I'm going to copy most of this down. So n times n minus 1, c sub n, x to the n minus 2 minus, and then this will become n c sub n x to the n. So I multiply x in, that means I'm adding 1 to an exponent of n minus 1, so that just gets me to the n. Okay. Next up would be an indices switch. So I'm going to focus in on the 3 parts here. And let's see. So let's do k equals n minus 2, which would mean n is k plus 2. And here we can just say k is equal to n for both of those. All right. And so what would that give us? All right, so that's k equals 0 to infinity. That would be k plus 2, k plus 1, c sub k plus 2 to the x to the k. All right, minus summation of k equals 1 of k c sub k and x to the k power, and plus 2 summation k equals 0, and that's c sub k x to the k. All right, so we got all of our exponents to match. That's good, but the problem we have now is our indices don't match. But that's a pretty easy solution to work around, especially if 2 of them start at 0 and 1 of them starts at 1. You just expand in, just plug in 0, evaluate at 0. So at k equals 0 for this first term, I would just get 2c2. And at the very last term, if I evaluated at 0, I would just get 2c0. So if I that'll allow me, so if I just bring the 2c2 and the 2c0 into it, then that creates a summation of k equals 1 for the rest of that. So I'm going to scroll over and copy over what I got so far, and then we'll continue. Okay, so now I've got all the summations starting at k equals 1. Ooh, I'm missing an exponent. So x to the k, whoops. So the summation parts match and the exponent parts match. So now I can combine them into a singular summation symbol. So 2c2 plus 2c0 plus summation of k equals 1 to infinity. And let's see, so we want k plus 2 times k plus 1 times c to the k plus 2 minus, and it looks like we have a k minus k. Ooh, you know what I want to do? I want to just factor that. So it's a minus k minus 2 c sub k. And feel free to convince yourself that my algebra is sufficient there. So, all right, so now what? Well, this whole expression equals 0, which tells us a couple of things. So that we know that 2c2 sub 2 plus 2c0 has to be 0, which implies that c2 has to equal negative c0. And then what else do we know? We know k plus 2 times k plus 1 c sub k plus 2 minus k minus 2 of c sub k has to equal 0. And so let's rewrite that with the later term in the pattern in terms of the earlier term. So that would be that the c of the k plus 2 term would equal k minus 2 over k plus 2, k plus 1, c sub k. All right. So now for the fun part. I don't know, is this the fun part? Fun part is just evaluating out terms of k. Keep in mind this fact will come up once we start expanding these things out. So we set up our k's and just start looking for any interesting patterns that show up. This particular problem has an interesting pattern when dealing with C0, C2, C4, basically even powers of k. There's an interesting pattern that shows up. So I'll kind of point that out here as I'm illustrating here. So I started off with k equals 0, evaluated it, and basically confirmed that C2 was equal to negative C0. Yay, that's what this that's what I showed. And then I plugged in 1 and I got a pattern there. But when I hit k equals 2, so when I got to right here, that's where this story got interesting. Kind of saved me a little bit of time going down the road there. So when I evaluated it at a 2, I actually get 0 over who cares, because it's 0. So it tells me my fourth c sub 4 is 0, and that showed up again over here at c sub 6. That term also is 0. So that means I only have 2 terms in the expansion related to c sub 0, and then everything else zeroes out. And then I've got, I just did a couple of terms for c sub 1 just to recognize that. So then we remind ourselves of our general expansion. So general expansion for solutions is going to look like C0 plus C1x plus C2x squared plus C3 x to the 4th keep expanding out there, and then I replace in what I discovered in my pattern, and at a certain moment I'm just plugging in zeros for essentially half of the terms. But I do have 2 terms connected to C0, and then the rest of the infinitely expanding pattern is connected to C sub 1. So when I separate out those 2, I get my 2 general equations. that look like this. So my first general solution based around c sub 0 or c naught is 1 minus x squared, and then the other equation based around c sub 1 is x minus 1 over 6 x cubed minus 1 over 20 x to the fifth minus ... pattern keeps continuing.